Let's go ahead and talk about what a partial derivative is. In Calculus 1 and Calculus 2, we're typically dealing with functions that have one input and one output. But in Calculus 3, or they like to call multivariable calculus, you're now going to be dealing with functions that have multiple inputs and one output. And one of the great things that come out of this is a partial derivative. So in single variable calculus, we're used to seeing a function like f of x, and if we want to study the derivative, we go ahead and find the tangent line touching at that specific point, and the slope of this tangent line represents the derivative of the function for any value of x. But in multivariable calculus and typically 3D images, we're dealing with two inputs, x and y, and has one output. And as you can see, these graphs look somewhat like hills or some mountains. And at any given point, the derivative can be found. And here's where the partial derivative comes in. Let's say you have a particular 3D image where two inputs, x and y, and you have one output. If we're going to take the partial derivative with respect to x, we're going to treat the y as a constant. We can visualize this by having y is equal to some constant so that you can see that at this particular graph, we're simply focused on how the x is changing at any particular point. In this particular case, you can see that the y is staying constant. And that's sort of the idea of how we take this derivative. We treat the other variable like a constant. Let me go ahead and show you. Let's talk about notation. If I wanted to take the partial derivative of this function f with respect to x, I need to draw this squiggly looking d, and it's telling me that I'm taking the derivative of the function f with respect to x. There's other notations like f sub x, and I've also seen this d sub x. But typically I like the first notation where you have that squiggly looking d. I mean, honestly, it's just aesthetics. So here I have a representation of the slice that we were talking about. Just imagine like y is fixed and I'm looking at the function in the x and z direction, and I'm trying to find the way it changes in the x direction. So if I'm going to take the derivative, I'm simply going to apply the same fundamental rules that we know. And in this case, we're going to do quotient rule. So there's my low function. And now as I'm going to take the derivative of this top function, keep in mind the y is constant. So just like 7 and y, those are both constants. So when I take the derivative of this, it is going to be 7y. I continue by subtracting by the first term. And now I'm going to take the derivative of the bottom term, which is simply e to the x squared plus y squared. And when I take the derivative, don't forget y is a constant, so that becomes 0. And now I go ahead and put this as the low squared. And just like a regular calculus class, I go ahead and just simplify this using some basic algebra. But as you can see, things do get a little more complicated, so you just have to keep track of your variables. And this is it. This is the partial derivative with respect to x at any given point xy.